The first thing we're going to cover today are the different types of addresses. Now, when we talk about computer addresses in general, we've got three types. On the physical layer is the MAC address. On the network layer, we have an IP address or a logical address. And then on the transport layer, we also have a certain type of addressing, and we call that port numbers. An IP address is a logical identifier, a unique logical identifier of a certain device or a host on a given network. So here we got two networks. This network right here is a private LAN network. And this network right here where we got two servers, an HTTP server and a DNS server, this now is a public network. And we'll talk about that later. But for now, notice that this is a public network and this is a private network. Then we have MAC addresses. Now the difference between this slide and the previous slide is only in the MAC addresses. So these devices now have MAC addresses. So MAC address is a physical identifier. An IP address is a logical identifier and a MAC address is a physical identifier. And a MAC address is also a unique identifier. So you can't have two repeated MAC addresses in the same network. And actually a switch, or to be more precise, a layer 2 switch, which doesn't speak the IP language, uses a MAC address to figure out where a certain device is located on a network. And the third type of addressing are port numbers. Port numbers help us distinguish between different services running on a certain host. For example, this host over here is going to use its port number 60,181 to send data to the DNS server, which is running on port 53. And it's going to use its other port, 30,524, to send packets to the HTTP server, which is running on port 80. So when the HTTP server sends packets to this host over here, it's going to use destination port 30,524, and then when the DNS server sends a packet to this host over here, it's going to use a destination port 60,181, while both of them use the same destination IP address. So that's the point of port numbers. We distinguish different services or different applications running on a certain host. And the last thing we're going to talk about in this lesson is IPv6. As you've probably heard by now, we're already out of IPv4 addresses, so IPv6 had to be developed as a solution to the IPv4 shortage. IPv4 actually only gives us around 4 billion addresses, while IPv6 provides approximately 340 trillion addresses. So we should be okay for some time. Now, here's one example of what an IPv6 address looks like, and here's a second one. So this is actually an address, an IPv6 address, which only has zeros in it. It's used, for example, for default routes. So you can actually write it like this. So I wanted to show you what they look like so that you're not scared of IPv6, but this course is meant to show you how to work with IPv4, and then maybe I'm going to create a course in the future on IPv6. Let me know if you'd like to see that. All right, so that will be it for the introductory lesson. See you in the next one. In this lesson, we're going to talk about binary numbers. Now, I know most of you are probably already familiar with all of this, but just in case, I want to cover all the basics. So the first number we're going to look at is going to be 0. So this is 0 in both the decimal and binary format. So the first digit we're going to look at is the far right digit. And in general, when we talk about binary numbers, we start from the far right. So the first digit on the right has a value of 1. The one next to it, the one on its left, has a value of 2. The next one is 4. The next one is 8, 16, 32, 64, 128, 256, 512, etc., etc. Hopefully you get the point. They double. When you move to the next digit is going to be 1024. So each one just doubles the previous value. Here's a simple table you can always use when working with binary numbers. So for example, when you get a 1, which is on the 4th place from right to the left, the value of that one is 8. When you look at the next one, the value of that one is 16. Let's look at an example. So here is a binary number. Now I'm reading from right to the left. It's 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 0. So what's the value of this binary number in decimal format? In order to calculate that, we're going to look at the values of ones in this binary number. So this one, 1 has a value of 2 because that's its place in this table. And then the next one has a value of 16. Let me see that. So this is 2, and we're going to add that. And then this is 16. We're going to add that to 2, so that's 18. And then we're going to look at the next digit, which is this one. That's going to be 128. We're going to add that to the previous sum. And then we're going to add these two ones, 512 and 1024. And in total, that's going to be 1682. Okay, so let's go to the next example. In this example, we're going to figure out a way to be faster in our calculation. Now, you can only do this if you get a batch of consecutive ones at the end of your binary number or at the beginning of your binary number if you're looking from right to the left. So how we're going to calculate this faster, that's the key word here, is we're going to look at the number to the left of our batch. The value of this batch is actually going to be the value of the next left number minus 1. So here we have 64, and the sum of all of these values is going to be 63. Now this is simple math and you can check it out yourself. This is what you're going to get each and every single time. So this makes the process easier for us because we don't have to add up every single value we have in this batch, but we know how much this is right away. So we're going to sum 63, 128, 1024, and 8192, and we're going to get the final value, which is 9407. And you can come up with any binary number that you want and practice this further. But we're going to continue to the next example, which is this. So you can pause this video and try and figure this out on your own because I'm just going to give you the results. Here's the results. Okay, so how we did this, we followed the previous examples and we just looked at the positions of ones and we added all of their values together and we got 726. So if you got that too, you're on the right path. That would be it for this lesson. See you in the next one. In this lesson, we're going to talk about the format of IPv4 addresses. So first of all, an IPv4 address has 32 bits or 4 bytes. That's 2 to the power of 32 different combinations. And that's approximately 4.3 billion unique addresses. Let's look at an example. Here's an IP address written in binary format. Here we can see that we actually do have 32 bits in an IP address. The first section has 8 bits.
The second one has 8 bits. The third one has 8 bits, and the fourth one also has 8 bits. We have 4 sections of 8 bits. Those sections are called octets because we have 8 bits in it. It's an octet. But this is just a binary representation. An IP address, an IPv4 address, is typically shown as 4 decimal numbers, which we can see here. So this is the example from the previous slide, and these are the decimal values of the same example. And these are the octets. We count the octets from left to right. The first octet is 98, the second one is 188, the third one is 19, and the fourth one is 71. But we don't really write an IP address like this. We add dots. We add dots between the octets, but we do not add a dot at the end of the fourth octet. Here's what this IP address looks like. It's 98.188.19.71. Now that we've talked about the singular octets, let's talk about portions in IP addresses. The first part of an IP address is always the network portion, and the second part is always the host portion. We can actually have one more portion in between. It's called the subnet portion, but we'll discuss that later. For now, just remember that you can't mix the two. So you can't use the first octet, for example, the first octet as the network portion, and then the second octet as the host portion, and then the third octet as network portion again. So you have to, once you're done with the network portion, the host portion begins and there's no more network portion in it. Now in this example, we have 2 octets that belong in the network portion and 2 octets that belong in the host portion. But it doesn't have to be like that. We can have 10 bits in the network portion and then the other 22 bits in the host portion. But we wouldn't be able to draw this like this. We would have to split the two. So for this example, or for what I've talked about up until now, this is only for /8/16 and /24 networks. And I'll talk about this format. It's called CIDR. We'll talk about this later, but for now, know that you can actually split one octet. You don't have to use an entire octet for a portion. Okay, now let's talk about the reason to split an IP address into 2 parts. Here we have a small network, 1 router and 3 switches. For the purposes of this example, this server farm or a small data center really is just a small network where we have 6 devices that require each 1 IP address at minimum. Each of these 3 networks is connected to an interface on this router. This interface is going to be the default gateway for all of the devices that are inside this network. This interface is going to be the gateway for these devices, and this interface is going to be the gateway for all of the servers that are in this network. Each of these interfaces is going to have an IP address. Let's look at those addresses. The gateway for the server network is going to be 10.0.1.1. The gateway for the second network is going to be 10.0.2.1, and the gateway for the third network is going to be 10.0.3.1. These are the network portions of each of these addresses. You can see that these are actually different networks. The point of the network portion is to differentiate different networks. Let's look at what IP addresses are going to be assigned to our end devices. The servers are going to have addresses like 10.0.1.10, 10.0.1.11, 10.0.1.13. I hope you can already see the part that's being repeated. So all of these devices are going to have addresses that begin with 10.0.1. That's the network portion. The network portion of an IP address is going to be repeated through the entire network. For this LAN, it's 10.0.1, and the host part changes for each device. The first IP address was assigned to the gateway, and then we reserved, that's the term used in DHCP, we reserved or we excluded the first 9 addresses from 1 to 9. And then we begin assigning addresses to end devices from 10 upwards. Now let's look at our second network. All of the devices have IP addresses like 10.0.2. something. The first laptop is 10.0.2.10, then the second one is 10.0.2.11. You can again notice the rule here. The network part is the same for all devices and for the gateway. In our third network, we got the same situation. The gateway is 10.0.3.1, and the end devices have addresses that begin with 10.0.3. Now that we've covered the types of addresses we would assign to gateways and end devices, we need to talk about 2 other IP addresses that are very important. The network address and the broadcast address. The network address is the very first IP address in a subnet. In the previous slide, we gave the first useful IP address, or the first usable, I believe is the term, IP address to our gateway, but that's not really the first IP address. The very first IP address in this subnet would be 10.0.3.0. Here we have an example, 81.2.0.0, where the first 2 octets are the network portion and the second 2 octets are the host portion. The network address has its host portion filled with zeros, and the broadcast address is the opposite. A broadcast address is the very last IP address in a subnet. Here's an example, 81.2.255.255. So 81.2 is the network portion, and 255.255 is our host portion. Hopefully you can notice our host portion this time is filled with 1s, and this is what it looks like in binary format. We have 8 1s in the 3rd octet and 8 1s in our 4th octet. Now let's look at some examples. The right part of this network is actually the same network from our previous example, but now we've added 1 router, which gives us 2 additional networks. We have this network between the 2 routers and this small LAN with 2 laptops. We're going to describe these 2 networks with their network addresses or their network IDs. This point-to-point network, a point-to-point network is a simple network between 2 routers. It's going to be 9000. So this is our network ID. The small LAN with 2 laptops is going to be 8000, and here are the end host IP addresses in these 2 networks. So we assigned the router on the left with 9001 and the router on the right with 9002. These are the two IP addresses we're going to use in this network, and in this network, we're only going to need 3 IP addresses, one for the gateway and one for each of the laptops. They're going to be 8001 and 80010 and then 80011. Now let's think about what are the network IDs for the 3 networks we had in the previous example. I'm just going to make this easy and display the network IDs. For the first network, it's going to be 10030, as we've talked about in the previous slides. So the network ID is the network portion of an IP address, and then the host portion filled with zeros. The other 2 networks are obviously going to be 10010 and 10020. The next thing we're going to talk about is what are these network IDs or network IP addresses actually used for. And the example I'm going to give you is going to be related to routing. So we're going to look at how do we build routing tables and what do they actually look like. So we're going to circle this 10.0. something network, and we're going to name our routers R1 and R2. We're also going to have to name the interfaces on our routers. So they're going to be interface 1 and interface 2 on router 1, interface 3, 4, 5, and 6 on router 2. And then we're going to look at what the routing table in router 1 looks like. A routing table lists the different networks that this router can reach. So router 1 can get to all these networks by simply sending packets to different interfaces. So a job of a router is actually to just get rid of a packet as soon as possible. Now, for example, if router 1 didn't have an entry for the network 10.0.3.0 in its routing table, it wouldn't be able to reach that network. So if it received a packet with a destination IP address that belongs to that network, it would just drop the packet because it doesn't really know where to send that packet. Fortunately, we do have an entry for that network, so router 1 is perfectly capable to send packets to that network. But now let's do something a bit advanced, and we'll cover this topic further in our future lessons. But I just want to show you what's possible with IP addressing and or IP subnetting in this example. We're going to look at this 10.0.123 network, and I promise to explain what this means further in probably the next lesson. But for now, just know that /16 means that the first 16 bits represent the network portion of this IP address of 10.0.0.0. So what I want to do here is I want to replace these 3 entries in our routing table with only this. Why can I do that? So when router 1 receives a packet with a destination address of 10.0.2.50, for example, okay, even if it doesn't exist here, let's say we add a new device here and we give it that address 10.0.2.50. So say that this laptop wants to send a packet to that imaginary device. Okay, so this router will look up the destination IP address, which is 10.0.2.50 in its routing table, and it's going to say, okay, so I have a route for 10.0.2.50. something, so anything. So this is a network address. It represents all hosts within 10.0.2 network. But before router 1 can reach this route, it has to go through all the other routes. So what I want to do is I want to simplify the process here. I'm just going to replace these 3 routes with one route. So this is basically called a summary IP address, but we'll talk about that later, I promise. But for now, what happens here is this router receives a packet with destination address 10.0. something. So the last 2 octets could be anything. So it doesn't have to go through 3 routes. Instead, it only goes through 1 route because anyway, it's going to send a packet with a destination address of 10.0. anything through interface 2. I hope that made sense. We'll talk about this further, but just to give you an idea of what's possible to do with IP addressing. And now we're going to talk about broadcast addresses, what they are, and to give an example of how they work. We've already defined our network IDs for all of our networks in our example, and I'm going to use the CIDR notation once again, and I promise that the next lesson is going to be about that, and we're going to do more examples. But for now, just know that /24 means that the first 24 bits, or 3 times 8, which is 24, or the first 3 octets represent the network portion. So 8.0.0 is our network portion, which is exactly 24 bits. So how do we figure out what's the broadcast address there? Well, we simply take the host portion and we turn it into ones in binary format. In decimal format, when we have 8 consecutive ones, that's 255. So the broadcast address here is going to be 8.0.0.255. So 8.0.0 is our network portion, and this last octet is our host portion. If it's filled with ones, it's going to be the broadcast address, and if it's filled with zeros, it's going to be the network ID or the network IP address. Now let's look at the other networks. So for 9.0.0.0/24, that's going to be, the broadcast IP address is going to be 9.0.0.255. Hopefully you can already guess what the broadcast addresses for the other 3 networks are. So we're going to use the /24 for all 3 of them, and all 3 of them are going to be the same network portion, and only the host portion is going to change from 0 to 255. Let's look at an example. Let's say that this laptop sends a broadcast packet with source address, its own address 10.0.3.12, and destination IP address is going to be our broadcast address for this subnet, which is 10.0.3.255. So once this laptop sends its broadcast packet, it's going to end up on the switch. The switch is going to send this packet through all of its interfaces except for the interface that received the broadcast packet. So these are the devices that end up receiving the broadcast packet. Now, if you're wondering what is the router going to do, is the router going to further forward this broadcast? It's not. So routers do not forward broadcast packets. Hopefully that's clear enough. We're just going to look at one more example of how to determine a network ID address and how to determine a broadcast address. So in this example, we're going to use host address 153.0.99.207. And this is the binary representation of this address. the red part is going to be our network portion, and the blue part is going to be our host portion. So to determine our network address, we're going to just copy the network portion, and into the host portion, we're going to put all zeros. So this is our network address. It's actually going to be 153.0.0.0. How do we determine the broadcast address? We're going to copy the network portion, and we're going to use ones instead of zeros in our host portion. There you go, guys. That's it for this lesson. We'll talk about network masks and the CIDR format and all of this further in our future lessons. See you there. All right, so I know I promised the next thing we would talk about would be CIDR, but before there was CIDR, we had classful IP addresses, and we really need to talk about those before we go any further. So I suggest we get right to it. At the very beginning, when we just started allocating IP addresses to computers, things were a bit different. Everyone thought that we would always be able to separate three sizes of networks: large networks, medium networks, and small networks. And the idea behind classes was that once a company or a university would want to get an address range, they would be given a range depending on the size of their network. So Class A networks were only supposed to be given to very large networks. And that is because in a Class A network, the first 8 bits or the first octet is the only octet that represents the network portion of that address. That means that there is only 256 Class A networks. One Class A network has 2 to the power of 24 different host addresses or different combinations for the host portion of the address. 2 to the power of 24 is somewhere around 16 million addresses. Now, hopefully you'll agree with me that there's probably not many networks in the world that actually need that many public addresses. The next class is Class B, which is somewhere between Class A and Class C. Class B networks have 2 octets representing the network portion of the address. The other 2 octets represent the host portion of the address. These were meant to be given to medium networks, and then Class C networks were meant to be allocated to very small networks. A Class C network is kind of opposite from the Class A network because Class C networks have its first 3 octets representing the network portion and only 1 octet representing the host portion. So one Class C network can only have 256 different IP addresses in one subnet. Now, one more thing, there are actually additional 2 subnets, classes D and E. D is reserved for multicasting and E is experimental and is used for research and documentation. Now let's look at some examples. Here's a Class A network 71.3.99.2. This is the network portion. So 71, the first octet, is the only octet that represents the network portion. The other 3 octets represent the host portion. Now, how do we determine the network address? So we take the network portion, we copy that, and then in the host portion, we put zeros. So 71,000 is going to be our network address for this example. Now, how do we determine the broadcast address? It's similar. So we also need to copy the network portion, which is 71. And then in the host portion, we're going to put all ones. Of course, this is in binary format. So when you convert 8 ones to a decimal format, you're going to get 255. So we're going to have 71.255.255.255. Now, how do we actually know to which class does a certain IP address or an IP range belong to? We determine that by looking at the first octet. So class A addresses are somewhere in between 1.0.0.0 and 126.255.255.255. So if we have the first octet ranging from 1 to 126, we have ourselves a class A IP address. Let's look at another example, this time from class B. 155.8.101.33. So in a class B network, the first two octets represent the network portion, and then the last two octets represent the host portion. So what is the network address in this example? Again, we're going to copy the network portion, which is 155.8. And then in the host portion, we're going to use all zeros. Of course, all zeros in binary format are the same in decimal format. So the network address is going to be 155.8.0.0. Now the broadcast address is going to be 155.8. That's the network portion. And in the host portion, we're going to use all ones. And just as in the previous example, 8 ones in binary format equals to 255 in decimal format. And how do we know that an IP address belongs to class B? So again, we look at only the first octet. And if the first octet is somewhere between 128 and 191, that is class B address. Let's see our third example, this time from class C. So here we have 201.65.4.137. Here, the first three octets represent the network portion, and only the last octet represents the host portion. As in the previous examples, we're going to determine the network address, and we'll get the network address by copying the network portion, 201.65.4, and then in the host portion, we're going to put 0. So that is our network address for this example. Let's determine the broadcast address. To determine the broadcast address, we're going to copy the network portion, and in the host portion, we're going to put all ones. Again, we're going to have 255 for each segment or each octet that represents the host portion, and since we only have one, it's going to be 255 at the end, and that's our broadcast address. Now, how do we know that an address belongs to class C? So once more, we look at the first octet, and if it's somewhere between 192 and 223, that's a class C address. Everything above 224 or everything above all IP addresses that start with 254 and upwards are going to belong to those two additional classes, class D and class E. Finally, as I promised some slides ago, here's the table that summarizes all 5 classes. As we've already learned in the examples, we recognize all 5 classes only by looking at the first octet. So here's the first octet, here's the second octet, here's the third octet, and here's the fourth octet. Class A addresses, or rather the first octet of class A addresses, ranges from 1 to 126. Then we skip 127, which is reserved for loopback, and class B starts at 128 and ends at 191. Class C begins at 192 and ends at 223. And let me clarify one more thing. So regardless of what the first octet is, each of these classes can have absolutely anything in the other octet. So it's only important to know what we have in the first octet. That is how we determine the class. All the other octets are just combinations of network portion and host portion of the IP address. All right, now that we're done with the table, let's go through some additional examples. So 200.200.200.200. Question for you is, which class does this IP address belong to? As we discussed, we only look at the first octet. So the first octet is 200. That, looking at this table again, would be class C. All right, let's go to the next example. 1.1.1.1. This is definitely class A. Next example is 192.168.1.1. This is probably the most familiar IP address, and it belongs in class C. Fourth example, 44.13.0.0. So this is also class A because the first octet is between 1 and 126. Fifth example, 100.0.0.255. This is also class A. And the last example would be 155.255.255.7. So the first octet is 155. Class A is between 1 and 126. Class B is between 128 and 191. So this IP belongs to class B. And that would be all for this lesson. See you in the next one, where we definitely talk about CIDR. As promised, in this lesson, we're going to talk about CIDR. CIDR stands for Classless Interdomain Routing, and we're going to start with an example right away. So we're going to use a Class B address from the previous lesson, and what we're going to do is we're just going to change its mask. First, let's go through this example. So this is a Class B address, 155.8.101.33/16. So /16 means that the first 16 bits of this IP address represent the network portion. So if we have 16 bits, that's 2 times 8, that's exactly 2 octets. Now to get the network address in this example, we're going to copy the network portion, and then in the host portion, we're going to put all zeros. And that's how we got 155.8.0.0. The broadcast address is just the opposite, so we copy the network portion, and then in the host portion, we put ones, and we get 155.8.255.255. At the end, we have a range of useful or usable IP addresses. This means that all of these addresses can be allocated to endpoints, to computers, to any device that's within this network. So the only 2 IP addresses that we actually cannot use in a range are these 2, the network address and the broadcast address. All right, now let's look at what happens when we change the mask. So here we had /16, and now we're going to use /21. Now we can't really separate the network portion and the host portion that easily. So these 2 octets are going to be the network portion, but then we're going to have some bits in the third octet that are also going to represent the network portion. And then the other half, or in this case, not the half, but the other, so we're going to have 11 bits in the host portion, so the other 11 bits are going to be the host portion. So for this example, we're going to need to write these numbers or this IP address in the binary format. Now it's a bit easier to distinguish the network portion from the host portion. So we're going to look at the first 21 bits. So this is 8 bits plus 8 bits, that's 16. And then we got 5 bits until here, and that's 21 bits. So the first 21 bits are going to be the network portion, and the rest is going to be the host portion. Now that we've got that figured out, how do we determine the network address and the broadcast address? So to determine the network address, we need to copy the network portion. So we're going to copy all 21 bits from the beginning of the IP address. Those are the bold numbers. And in the host portion, we're going to switch all the bits from the IP address to zeros. So this is the network portion. We're going to copy the first octet, which is 155, that hasn't changed. And then we're going to copy the second octet, which is 8, and that hasn't changed either. But the third octet has changed. So in the third octet, we had 101 at the end. And this 1 has a value of 1. This next bit has a value of 2, but that's switched off, so we don't count that. And then the next bit to the left is 4, and that's turned on, so we do count that, and that's 5 in total. So we need to calculate 101 minus 5, and that's going to be 96. Or you can add these two values, these two ones, which are 64 and 32. Either way, you get 96. And then in the fourth octet, we're going to have all zeros, and that's easy. That's just 0 in the decimal format as well. Now let's look at the broadcast address. So for the broadcast address, we're going to copy the network portion, and that's going to be 155 and 8 for the first two octets. That doesn't change. But then the third octet changes because we're going to put ones in the entire host portion. And that's going to be 103 when we add all of these up. And the fourth octet is going to be 255 because we have 8 ones in the binary format, which is 255 in the decimal format. Now to determine the range, we're just going to go from the next address from the network address and all the way up to the one address that comes before the broadcast address. So the range is going to be from 155.8.96.1 to 155.8.103.254. All right, hopefully that clears up CIDR. We're going to do more examples later, but now we need to cover one more thing. So it's super easy to write a mask like this, but actually when you configure a router or a switch or some servers, you can't really use this format while configuring. So a mask can actually be written the same way as an IP address. 21 equals to 21 ones and 11 zeros. And the way you would write that or type that in when configuring a router would actually be like this. You would translate the binary numbers into decimal values, and that would look like this. So we have 8 ones, which is 255, and then another batch of ones, which is also 255. And then we have 5 ones, and when you add all of those values, that's going to be 248. And then you have 8 zeros, which is going to be 0. So this is what configuring an IP address with /21 mask would look like on, for example, a Cisco router. All right, that will be it regarding CIDR. As I said, we're going to practice some more, so don't worry, just continue to next lessons, and hopefully things will start clearing up. Before we go on to talk about subnetting, we need to discuss reserved IP addresses, because not all IP addresses are equal and not all of them can be used freely. Some of them are reserved for specific use. For example, all zeros are used as a default route. All ones in binary format and in decimal format, it looks like this. They are used as a default broadcast. So in our previous lesson, we determined broadcast a bit differently, but you can always use this form for sending broadcast packets all once in a binary format and of course in decimal format. That's what this looks like. And then we have the loopback address range. Most of you are probably already familiar with the address 127.0.0.1, but actually an entire A-class range is reserved for this use. Then we have the APIPA addresses. APIPA stands for Automatic Private IP Addressing, and it's used when your computer is set to ask for DHCP parameters from a DHCP server, but can't really find a DHCP server, or maybe you're not connected to a network, so you can't get to a DHCP server, or it doesn't exist, etc., etc. So when your computer can't get an IP address any other way, it's going to assign an APIPA IP address to itself. Other than that, we also have 3 private network ranges. These are defined in the RFC 1918. RFC stands for Request for Comments, and these are the documents where you'll find pretty much all of known network and other computer-related standards. So the 3 ranges are 10.0.0.0/8. Of course, we've learned in the previous lessons what this means. So pretty much all of the addresses that start with 10 or which have 10 in their first octet are part of one of these 3 private network ranges defined in this RFC. The next one is 172.16.0.0/12. And now it's not that easy to differentiate between octets when we talk about this mask. So I'm going to show it here in binary format. This is not really correct because this would be /16, the way it's shown here. But it's correctly shown in this binary representation. So the first 12 bits of this IP address represent the network portion. So this range actually ranges from 172.16.0.0 to 172.31.255.255. So you can calculate that based on what we've learned so far and check if I'm right. But that's it. That's the second private network range. And the third one you've also probably heard of. It's 192.168.0.0/16. So all of the IP addresses that have 192 in its first octet and 168 in its second octet, and whatever they have in the other two octets, they belong to a private network. Okay, now let's talk about the difference between public and private networks, or public and private IP ranges. So these three ranges that you see on the screen right now, these are only meant for private networks. This means that these addresses cannot go out into the internet. So they're not routable on the internet. They shouldn't end up in the internet. So there should be no packets in the internet with any of these addresses in the source IP address field or destination IP address field. So these don't exist on the internet. How is this achieved? Well, by using NAT. NAT is network address translation, and it helps us translate our private IP addresses into public IP addresses that are actually allowed on the internet. So the private IP addresses we talked about in the past couple of minutes, they're not even allowed on the internet. So we have to use the public IP addresses. So we have to translate our private IP addresses. The reason why we need to do this is because there are not enough public IP addresses out there for all of us to have one IP address, one public IP address per device or per person. So we have to use private IP addresses in order to save public IP addresses. And then we use public IP addresses. For example, these three computers are going to use one public IP address to go out to this HTTP server or web server in this example. So this server is going to see all three of these computers coming from a single public IP address. So this is how that's achieved. We have a private interface on the router. This is the LAN interface, and its IP address is 192.168.1.1. And we've talked about this in the previous slides. The network part, or the network portion of the IP address, has to be the same in the entire network. So this is our private facing or private network facing interface on our router. And this is the public network facing interface, or the WAN interface, wide area network interface. And we're going to give it this address, 76.0.13.6. So this is definitely a public IP address. It doesn't belong to any of the three ranges we've talked about on the last slide, and it's not a reserved IP address, so we can use it freely as a public IP address. Now this computer, 192.168.1.5, is going to send a packet. And this packet has a source IP address 192.168.1.5. That's the IP address of this computer. And the destination IP address is going to be 85.202.9.3. That's the IP address of the web server. So when this packet reaches the switch, the IP parameters remain the same. And then when this packet reaches the LAN interface on the router, the IP parameters are still the same. They only change when this packet reaches the WAN, or the outside facing interface of the router. So the source IP address changes from the private IP address to the public IP address. And then this packet is routed through the internet, and finally, when it reaches the HTTP server only sees the public IP address, and it's going to be the same public IP address whether the packet is sent by the top computer or the middle computer or the bottom computer in this example. Now when the server sends its response, its source IP address or the source IP address of the response or of the packet is going to be the IP address of the web server. So it's going to be 85.202.9.3, and the destination IP address is still going to be the public IP address of the router. So once that response reaches the public interface on the router, the IP parameters are still the same. It's only when the packet actually goes through the router is when it's NATed back into the private IP address. So, whoops, I went back. So this is what happens next. Do you see that? So the source IP address remains the same, but the destination IP address is changed from the public IP address to the private IP address. And then the router sends the packet back to the original sender, which is 192.168.1.5 computer. Okay, now that we've covered the basics, let's talk about why do we even need subnetting? Let's look at an example. So here we have a network with a router and 3 switches that are all connected to each other, and then they're connected to a single interface on a router. For this example, we're going to use a class A network 10.0.0.0/8, which means that only the first octet represents the network portion and all the 3 other octets represent the host portion. That means that we can have 2 to the power of 24 different IP addresses. Now, I'm not going to populate all of the computers with IP addresses, but let's say they have something like this. And we're going to talk about an example when one of the computers sends a broadcast packet. So here we have a computer with an IP address of 10.0.0.70, and this PC is going to send a broadcast. So what happens next is this packet goes to the switch. Now, a general rule is that once a switch receives a broadcast packet, it will forward this packet to all of its ports except the port where it received the packet. So what we will see here is that this switch in the middle is going to get a packet, and then all of the other laptops in this switch's network are also going to receive this broadcast packet. Now, the middle switch is also going to forward the packet to all of its ports except back to the port where it received the packet. So this packet is next going to go to the router, the switch to the right, and all of the laptops in the middle switch's network. Now, the router is not going to forward the packet because routers generally do not forward broadcasts, but this switch is going to forward the packet to all of these PCs, to all of the PCs in its network, I should say. So in the end, these are all of the devices on this network that have received this broadcast. Now, you may notice that it says security here, and this is a security concern. Generally, broadcast is an enemy of security because the way a network functions normally is that when a computer receives a packet that isn't meant for that computer, is going to drop it. But then if you install, for example, Wireshark or any other sniffing program on a computer, it is going to read all of the packets that it receives, even if that computer wasn't meant to be a destination of that packet. But enough of talking about problems, let's talk about solutions now. I'm going to suggest 2 solutions to this issue, and the issue is a too big network. So we want to segment this network into smaller parts. One way we can do that is using VLANs. VLAN stands for Virtual Local Area Network, and it's used to virtually separate different logical segments of a network. In this example, I used 3 VLANs. 10.0.1.0, 10.0.2.0, and 10.0.3.0. And these three networks are appropriately named VLAN 1, 2, and 3. You will notice that all of them are /24, which means that they all belong in different subnets. So this is one subnet, and then this is another subnet. And we know that by looking at their network portions. If two IP addresses have different network portions, that means that they are different subnets. So when you look at colors behind laptops, in the first network, we have 6 laptops in VLAN 1. In the second network, we have 2 laptops in VLAN 1. And then in the third network, we have 5 laptops in VLAN 1. So if one of these laptops, let's say this one, sends a broadcast packet, all of the green laptops or all of the laptops that belong to VLAN 1 are the only laptops that are going to receive that broadcast. So even if all of these other laptops are in the same network or are connected to the same switch, they're not going to get that broadcast because they belong to different networks, at least virtually. So that's what you get when using VLANs. Now, the second solution is going to be to physically separate these networks. So we're going to delete the links we have between these switches, and we're going to instead connect each switch to a separate interface on a router. Now, you can't have 2 or more interfaces on a router that belong in the same network. So if you want to have a topology such as this one, you will have to give each interface on a router an IP address that belongs to a different subnet. In this case, the first network or the green network is going to be 10.0.1.0/24. This is the network IP address. And then to the interface of that network, we're going to assign, for example, 10.0.1.1. People or network administrators usually assign either .1, .10, or .254, which is the last usable IP address in an IP range. But for example, let's say that we can give .1 to interfaces. So all of these interfaces can be .1 in the host portion, but then they're going to belong to different networks because their network portions are different. So let's say that the green network interface is going to be 10.0.1.1, and then the yellow network interface is going to be 10.0.2.1, and the blue network interface is going to be 10.0.3.1. Now, the computers or the laptops can have, for example, this one can have 10.0.1.10, and this one can have 10.0.2.10. It doesn't matter that their host parts are the same as long as the network portion is different. So technically, they belong in a different network or they belong to different networks. If that computer or this first computer in the green network sends a broadcast packet, the only devices that are going to receive that packet are going to be the green laptops and the interface, the first interface on our router. There are 2 types of subnetting we're going to learn in this course: fixed length subnet mask subnetting and variable length subnet mask subnetting. First, we'll talk about fixed length. Fixed length means that every subnet in your network will have the same mask. In the example from our previous lessons, whether we use fixed length or variable length subnetting, we will end up having the same mask for each of these 3 networks. Let me explain this example real quick. So we'll look at the first subnet. What's going on with my cursor? Here it is. Okay, so let's look at the first subnet, 10.0.0.0/27. So we have 15 laptops in this subnet. That means we need 15 different IP addresses to be assigned to our laptops. We need one more address to be assigned to our router interface. But we need two additional IP addresses for the network ID or the network IP address, and the second one for our broadcast IP address. That means in total, we need 18 different IP addresses per subnet. So each of these networks, each of these subnets needs at least 18 different IP addresses. If we use /27, that means we'll get 32 IP addresses per subnet. How did I get that number? Well, /27 means that the first 27 bits represent the network portion of the IP address, and then the remaining bits, which is 5, represent the host portion of the IP address. So 2 to the power of 5 is 32, which means that we can have 32 different combinations to be used as the host part of the IP address. Let's go to our next example. So here we have 3 smaller networks and 1 larger network. Of course, in all of these examples, the cloud that represents the internet is just going to be ignored. It's just there, and it could be any network. Let's start by counting the number of IP addresses we need per subnet. So we'll start from the largest network on the left. We need 8 IP addresses for 8 laptops, plus 1 IP address for the router interface, plus 2 IP addresses for the network ID and broadcast. In total, that's 11 IP addresses for the largest network. For the other 3 networks, we need 2 IP addresses for the 2 laptops, plus 1 IP address for the router interface, plus 2 IP addresses for network ID and broadcast. In total, that's 5 IP addresses for all of these networks. So this is our request. Create 4 subnets where 3 subnets should have 5 IP addresses each and 1 subnet that needs 11 IP addresses. And here I'm going to give you the solution right away, and then I'll walk you through that solution. The first thing you should notice is that each of these 4 networks that are different have the same mask. Okay, so how did we get here? First, I'm going to mark all the subnets and then populate the number of hosts. We're going to begin from the largest network, which needs 11 IP addresses, and then we're going to talk about the other 3 networks that need 5 IP addresses each. The next thing to be determined is the mask. So in fixed length subnetting, all of the subnets are going to have the same mask, and the masks for all of the subnets is determined by the largest network. So we just need to make sure that the largest network has enough different IP addresses to cover all of its hosts. For 11 addresses, we're going to need 4 bits. 2 to the power of 4 is 16. If we used 3 bits, that wouldn't be enough. 2 to the power of 3 is 8. So that's not enough for our largest subnet. If we were to use 5 bits, that's too much. That's wasting IP addresses, because that's 2 to the power of 5, that's 32. That's 32 different IP addresses. We need 11, and we can get 11 by using 4 bits. So that's what we're going to do. Mask /28 is perfect for us because that means we'll use 28 bits for the network portion and the remaining 4 bits for the host portion. Again, 4 bits is enough because 2 to the power of 4 is 16. Now we'll just copy that into all the other subnets. Since this is fixed length, all of the subnets have the same mask. Our remaining fields are going to be network ID, which is the network IP address. And then the other or the last column is going to be range of useful addresses. So the network ID we're going to begin with is 192.168.1.0. Range of useful IP addresses will begin at 192.168.1.1, and the last useful address is going to be 192.168.1.14. 192.168.1.15 is going to be our broadcast address that we can't allocate to a host or a router interface. So the next network ID, the network ID for our second subnet is going to be 192.168.1.16. And don't worry if you're not sure how I got here. I'm going to explain this when we go through our more complex examples later. But for now, since these are very small subnets, you can see it for yourself by using simple math. So 2 to the power of 4 is 16, as we've said at the beginning. And here we have actually used exactly 15 IP addresses, or exactly 16 IP addresses counting the 0. So it's the 0th IP address, and then the other 15 are going to be 14 useful IP addresses, and the 15 is going to be broadcast. So the next IP address is 192.168.1.16, and we're going to use that as the network ID for our second subnet. Range of useful IP addresses in the second subnet is going to be the next 16 IP addresses as in the previous example, from 192.168.1.17 to 30. And then 31 will be the broadcast IP address for the second subnet. And then the network ID for the third subnet is going to be 192.168.1.32. And then again, we're going to use the next 16 IP addresses in that subnet, where 192.168.1.47 is going to be broadcast, and then 192.168.1.48 is going to be the network ID of the fourth subnet. And then the range of useful IP addresses for that subnet will be from 192.168.1.49 to 192.168.1.62. And the broadcast IP address there is going to be 192.168.1.63. And if in this example we had a fifth subnet, then the network ID for that subnet would be 192.168.1.50. So as you can assume, this is very, very basic. In the following lessons, we'll go through more complex examples. So just keep going and you'll be a pro very, very soon. Time to talk about VLSM. VLSM stands for Variable Length Subnet Mask, and the goal of this type of subnetting is to save as many IP addresses as possible. Let's look at the definition. So, unlike fixed length subnetting, variable length subnetting creates a hierarchical IP address space, making it possible to create subnets without wasting a large number of addresses. We're going to use the same example we used in the previous lesson, only this time we're going to adapt the mask when we get to the smaller networks. So we're not going to use the same mask for all 4 networks. So the request was to create 4 subnets where 3 subnets should have 5 IP addresses each, and 1 subnet needs 11 addresses. Let's remind ourselves what was the solution when we used the FLSM technique. We had 4/28 subnets, which means each subnet has 2 to the power of 4, which is 16 different IP addresses. And only in the first subnet, we actually needed that many IP addresses. In the other 3 subnets, we only needed 5 IP addresses. So let's look at the VLSM solution. Now for the first network, it's still going to be /28 because, as I said a minute ago, we need 11 addresses in the first subnet. So we're going to use /28 because that gives us 16 different IP addresses. The network ID also remains the same, so it's going to be 192.168.1.0, and the range is also going to go from 1 to 14. Dot 15 is going to be the broadcast IP address. Now let's determine what's going to be the mask for the second subnet. The second subnet, just like the other 2, need only 5 IP addresses. So we can give it /29 because that gives us 3 bits for the host portion, which means we can create 2 to the power of 3, which is 8, different IP addresses for hosts. The network ID is again going to be the next free IP address after the broadcast IP address in the previous subnet. So the broadcast address was 192.168.1.15. So the network ID for the second subnet is going to be 192.168.1.16. The range will be from 117 to 122 because this time we're only going to use 8 IP addresses. So for the other 2 subnets, it's actually going to be easy because the mask is the same. We only need to calculate the range. So for subnets 3, mask is /29. The network ID is going to be the next free IP address after the broadcast address of 192.168.1.23 from the previous subnet. And the range is going to go from 25 to 30. And then 31 is going to be broadcast for subnet 3. So the network ID for the fourth subnet will be 192.168.1.32. And the range is going to go from 33 to 38. Let's compare our VLSM result with the FLSM result. So this is FLSM and this is VLSM. When you look at the last IP address we used in the fourth subnet for FLSM, it was 192.168.1.62. And then the fourth subnet, or the last IP address in the fourth subnet, when we used VLSM, was 192.168.1.38. So this shows you how many IP addresses we actually saved only by using the VLSM technique. One last topic we need to discuss is summarization. I'm going to explain summarization through an example, and we'll use a network we used in our previous lessons. All right, let's say that our router, the only one that we have in our network, instead of being connected to the internet, it's connected to another router, and then that router is connected to the internet. We're going to assume the IP addresses that we decided to give these networks in our previous lesson. So the network between the router and the switch on the left is 192.168.1.0/28. And then the 3 switches that have only 2 laptops connected to each one of them are /29 networks. And then we have another network between the 2 routers, between our old router and our new router. That's going to be 192.168.1.40. And notice that if we have a /29 here in this network, 192.168.1.32/29, that means that our last usable IP address in this subnet is going to be 39, and that's going to be the broadcast. So the next network ID, or the next network IP address, is going to be 192.168.1.40. And we're going to give it /30 because this is a point-to-point network, and a point-to-point network between two routers only needs two usable IP addresses, one for the interface on the first router and the other one on the interface on the second router, and then we need the network ID and the broadcast IP address. And with /30 network, that's what we get. We get exactly 4 IP addresses. The only network left to define is our public network, which is the network between our new router and the internet. So we're going to use 777.0/30. Now let's separate our private network from the public network. So this area right here is our private network. Now, if we were to look at this network from the internet, and just for the sake of this exercise, let's forget about these IP addresses actually not being routable on the internet. So if we had a router someplace on the internet, it would have to know about all of these subnets. So it would have to remember a route for 192.168.1.0/28, 192.168.1.16/29, 124/29, 140/30, etc., etc. In order to avoid that, we could just say to that imaginary router, all of the addresses or all of the networks that begin with 192.168.1 are here. So they are on this side of this public router, so to the left. So the only thing you need to do is just send a packet to this router, and then this router is going to know where all of the specific subnets are. The problem with that is if we had, for example, 192.168.1.128/30, for example, network somewhere else on the internet. So that would be an issue because we would have said to that imaginary router, okay, all of those networks are here. But then if one of those networks such as 128 or 192 or something like that appeared someplace else, then our routing would be incorrect. Because of that, we're going to scratch our /24 mask, and we're going to create a more specific mask to only cover those IP addresses that are in our private network connected to this router. What we're going to do is we're going to look at all of the networks that we have in this network, or all of the subnets that we have in this network. So it's 192.168. All of the subnets have their first octets like this, 192.168. And then they also have 1 in their third octet. But then the fourth octet is different in every subnet. We're just going to look at the network that has a highest value in its fourth octet, and that's this network, 192.168.1.40. So we need to think about what's the last usable IP address in this subnet, and that's 43. So 40 is the network ID, 41 and 42 are the two usable IP addresses, and then 43 is broadcast. Okay, so here we have all zeros, and this is our definite network portion if the mask is /24. But then this value is 43 in decimal format. And in order to create a summary subnet or a summary IP address, we need to look at all of the bits that are the same in all of our subnets. So it's definitely going to be 192.168.1. We can already see that without doing any math. But then the first 2 bits in our fourth octet are going to always be 0. That means that the number of bits that are always the same in all of our subnets is going to be 24. So this is 24 plus the 2 bits from the fourth octet. So that's 26. And that's going to be our new subnet mask. So 192.168.10/26 is our summary address for this entire network. Now we are safe in case a new network appears. For example, let's say that's network X and its subnet is 192.168.164/26. So now we're okay because all of our IP addresses in our existing network or our existing summarized network are going to range from 192.168.1.1 to 192.168.163, which is actually what you would get if you would try and make a broadcast IP address for this subnet. So if this were one simple subnet and you knew nothing about it, just looking at it from the outside, and you try to get its broadcast address, that's the last IP address in this subnet, it's going to be 163. So the very next IP address, which is 164, is a perfectly usable IP address that can be used in any other subnet. So the range for this new network X would actually be 192.168.165 to 127. So we're perfectly safe to use this summarized IP address. But don't worry, we're going to practice some more, and we're going to go through some more examples in our future lessons. Let's dive into our examples. We're going to begin with subnetting a Class A network using FLSM. In the first example, we need to divide a Class A network 50.0.0.0 into two equal networks. We're going to need two identical networks, and then we're going to have to determine network address for each of those networks, first usable address, last usable address, and a broadcast address for both of those networks. Then we're going to look at the binary format of each of these addresses, and then we're going to transfer that into the decimal format. First, let's calculate the binary value of our Class A IP address. The first bit, which has a value of 128, is going to be switched off because we don't need it. The second bit is 64, and we don't need that either. The third bit from left to the right is going to be 32, and we're going to need that. So that bit is going to be turned on. The next one is 16. 32 plus 16 is 48, so we need that too. The next one is 8, and if we added that to 48, that would be 56. That's too much. The next one is 4, which is also too much if we add that to 48. And the next one is 2. We're going to need that. 48 plus 2 equals 50. And then the last bit is 1. Obviously, we're not going to need that one. And we've got ourselves our first segment or our first octet of our IP address. The next three octets are going to be all zeros, so that's easy. The first 8 bits in this IP address are going to be the network portion. And we know that because all Class A networks are /8 networks. Now, in order to divide this network, we're going to use the first bit after the network portion. We're going to take this bit and join it into the network portion, into the existing 8 bits. So now we're going to have 9 bits representing the network portion. Now, even though this 9th bit is the part of the network portion now, or it's part of the new network portion for the new 2 subnets, it's still going to be 0. So our network address for our first subnet is going to be 50.0.0.0. Our first usable address is going to be the same as this, but we're going to switch the last bit to 1. So we're going to copy all the previous bits, and then we're just going to use 1 at the end. There it is. So the decimal representation of that address is 50.0.0.1. Now our last usable address is going to be the opposite of that. So we're going to take our first 9 bits, which represent the network portion, and we're not going to change that, but we are going to change the remaining bits to ones, except for the last bit. If we use 1 in our last bit also, that gives us our broadcast IP address. So the last usable IP address is actually going to be the broadcast address minus 1. So this is what that will look like. We copy the network portion, which are the first 9 bits, and then we use all ones, but the last bit is still going to be 0. And in decimal numbers, that's going to be 50.127.255.254. The broadcast address is going to be, as I mentioned earlier, literally just the next IP address after the last usable IP address. And in decimal numbers, that's going to be 50, 127, 255, 255. For our second subnet, we're going to have to switch our 9th bit from 0 to 1. Actually, this bit could be called the subnet portion. So in this example, we actually have 3 portions. We have the network portion, the subnet portion, and the host portion. So this subnet bit is 0 for the first network and is going to be 1 for the second network. That's going to be, if this is 1, our network address is going to be the first 8 bits, or the first octet is still going to be the same, but then the 9th bit is going to be 1. And then the rest of the bits for the network IP address are going to be zeros. And in decimal format or in decimal numbers, that's 50.128.0.0. To determine our first usable address, we're going to copy the network portion, and then we're going to use all zeros, but for the last bit. For the last bit, we're going to use 1. And in decimal numbers, that's 50.128.0.1. The last usable IP address is just going to be the opposite. So instead of using all zeros after the network portion, we're going to use ones, except for the last bit. The last bit is going to be 0. And in decimal numbers, that's 50.255.255.254. The broadcast IP address is just going to be the next IP address, which is 50.255.255.255. Welcome to subnetting a Class A network using FLSM, example number 2. This time, we need to subnet a Class A network, 21000, and the question is, how many Class C networks can we create? Right now, we have a network 21000 where only the first octet represents the network portion. We need to create Class C networks, which means that the first 3 octets will represent the network portion. So the first network here is going to be /8, and that's a Class A network. And the second network is /24, and that's actually a Class C network. Our task here is actually pretty simple. We only need to calculate the number of combinations we can get from these two octets in the middle. So in a class A network, the first octet is going to be the network portion, and we can't change that because that's defined in the requirement. We get a class A network 21000, and the network portion you can never change. So the only part we can change are these two octets in the middle, and that's 2 to the power of 16. So that is our answer. That is the number of class C networks we can create out of any class A network. I'm actually going to try and prove that to you. So we're going to look at the binary representation of our network 21000, and we're not going to change the first octet and the last octet. So the first octet we're not going to change because we can't change it. That's what we got in the requirement. So that's our class A network, and the network portion we can't change. For example, if we're a company or I don't know, an internet service provider or anything like that, and we buy this network. So we are assigned 21000, and we can change the host portion, the original host portion, but we can't change the original network portion. So we're going to use the middle two octets as a subnet portion. The first octet is going to be the network portion. The second and the third octet are going to be our subnet portion for our C networks. And then in all of our C networks, the last octet is going to be the host portion. So of course, we're going to be changing the host portion to assign specific IP addresses to specific endpoints or hosts or whatever. But for subnetting purposes, we're not going to change that last octet. So for example, the first class C subnet is going to be 21000. The second one is going to be 21010. The third one is going to be 21020, etc., etc. It's going to be 2, 3, 4, and then we're going to go all the way to 255 in the third octet. Once we've filled the third octet for the first time, we start changing the second octet. So now the second octet is going to be 1. It's going to be 21100. And then we start filling out the third octet all over again from 1 to 255. Once we've reached 255 for the second time in the third octet, we're going to start increasing the second octet. It's going to go to 2, 3, etc., etc. Our last class C subnet in this example is going to be 21255 0. So we're going to go all the way from 21000 to 255 0. So hopefully you got the point. We start changing the third octet first, and then once we've filled out the third octet for the first time, we change only one bit in the second octet. And then we start filling out the third octet all over again. And then when we fill it up again, we change one more time the second octet. And we continue to do that until we get all ones in binary value, of course, in the second and third octet. All right, this time we're asked the same question as in the previous example, only here we have a class B network. So how many class C networks we can create out of a single class B network 155.3.0.0? So in a class B network, our subnet mask is /16, which means that the first two octets represent the network portion. In a class C network, the first 3 octets represent the network portion. So the difference in this example is only 1 octet. And our answer is pretty obvious here. It's 2 to the power of 8. If we try and do the same thing we did in the previous example and go from the first subnet to the last subnet, it's going to look something like this. So the third octet, or our subnet portion, is going to go from 0 to 1, 2, 3, 4, etc. And then when it's up to all ones, that's 255. And that is our last C network, or C subnet in this example. Subnetting a class B network using FLSM, example number 2. This time, we've been allocated a class B network address of 189.2.0.0. And we need to create at least 9 subnets with 64 addresses, and then 5 subnets with 100 addresses, and then 13 subnets with 70 addresses. Now, to clear this up, we're not looking to create 9 subnets with a total of 64 addresses, but 9 subnets with 64 addresses for each of those 9 subnets. So for example, for these 5 subnets with 100 addresses per subnet, it's going to be a total of 500 addresses for all of those 5 subnets. The way we do this is, first, we need to find a common subnet mask that satisfies all requested subnets. And then we need to count the number of subnets needed. So for our first task, we're going to look at the largest subnet, and that's obviously the 100 addresses subnet. If we satisfy the largest subnet, we're going to satisfy the smaller subnets. So we need to figure out how many bits we need to use for our host portion to be able to create at least 100 different addresses. That's going to be 7 bits, because 2 to the power of 7 is 128. If we used 6 bits, that would be 64 different addresses. And that's actually enough for these 9 subnets, which require 64 addresses each, but it wouldn't be enough for the other 2 types of subnets. If we use the 7 bits for the host portion, we are left with 25 bits for the network portion. But we got a class B network, which means that the first 16 bits are never going to change. So that's our default network portion. The bits that are left in between our network portion and our host portion is going to be our subnet portion. That brings us to our second task, which is count the number of subnets needed. So we need 9 subnets, and then 5 subnets, and then 13 subnets. In total, that's 27 subnets. Now we just need to make sure that we can fit the 27 subnets into our subnets portion. And this portion has 9 bits, which means that we could actually create 512 of these subnets. So our answer to this requirement is, if we use 189.2.0.0/25, we could create all of these subnets. That's pretty simple, so let's look at an extra question. Let's name the first, the 11th, and the last subnet. The first one is obvious. It's going to be 189.2.0.0. 11th is a bit trickier. Let's go from the first. So this is the first, where we have all zeros in the subnets portion. And this is second, and then this is third. But we can't keep on going like this. What if you get asked, what's the 100th subnet out of 1,000? So we need to automate this. Let's look at it this way. If our third subnet has a value of 2, but we're looking at these 9 bits as if there is no dot. So if our third subnet has a value of 2, then our 11th subnet will have a value of 10. And this is going to be the value of 10 if we use 9 bits to write it in binary format. So this is our 11th subnet. If we wrote this in decimal format, this one has a value of 1 in this one octet. In this third octet, this is 1, and then this is 2 that switched off, and then this is 4. So our 11th subnet is going to be 189.2.5 in the third octet, and then 0 in our fourth octet. And this is, of course, /25. Finally, for our last subnet, so we said that in total we have 27 subnets, so we're looking at the 27 subnet here. So the 27 subnet is going to be 26 in binary format in our subnets portion. If we look at these 9 bits, this 0 is 1, and then this 1 is 2, and then this 0 is 4, and then this 1 is 8, and then this 1 is 16. When we all add all of those up, that's going to be 26. But then when we look at this octet, these are different values. So this is 1, and then this is 4, and then this is 8. In total, that's 13. So our 27th subnet is going to be 189.2.13.0. And of course, that's going to be with /25. This time, we're going to use FLSM to subnet class C networks. We're going to go through several simple examples. In the first example, we need to answer how many subnets can we fit into a class C network if each subnet has at least 10 addresses. Let's think about this for a second. If we need 10 addresses per subnet, we need to figure out how many bits we're going to use for our host portion. In order to create at least 10 addresses per subnet, we're going to need 4 bits for our host portion. 2 to the power of 4 is 16. If we used 3 bits, that wouldn't be enough because 2 to the power of 3 is 8. So we're going to use 4 bits for our host portion. That means we're left with 4 bits for our subnets portion. Since we started with a class C network, which is /24, which means that 24 bits are going to be used for the network portion, and we've decided to go with 4 bits for our host portion, we're left with 4 bits for our subnetting portion. So in our subnetting portion, we can create 16 different combinations or 16 different subnets. Let's look at an example. Let's say we started with 10, 10, 10, 0, /24, of course. So in binary format, that would look like this. If the first 24 bits are the network portion, and we use the last 4 bits for our host portion, we're left with 4 bits for the subnetting portion. In total, that's 16 different subnets with 16 addresses per subnet. Now we're going to take this answer and these 16 subnets that we have right here, and we're going to look at some further questions. Question number 1. Is address 10.10.10.72 in the same subnet as 10.10.10.80? Let's look at what these 16 subnets look like. So the mask for all of those subnets is /28. A short reminder here. We started with /24 because we had a class C network in the beginning. And then we decided to use 4 bits for our host portion. and 4 bits for our subnetting portion. So the subnetting portion becomes a part of the network portion. So we're going to use /28 because we had 24 bits in the network portion plus the 4 bits we used for subnetting. Okay, so subnet number 1 went from 10, 10, 10, 0. And with /28, it means that the broadcast IP for this subnet was 10.10.10.15. Because when you take the host portion, which was 4 bits, and fill that with 4 ones, that's 15. Let's have a binary format down here to make it easier. So this is what the first subnet network ID is. 10.10.10.0. The second subnet network ID is going to be the next address after the broadcast address from the first subnet, which is 10.10.10.16. And let's look at what that looks like in the binary format. So we just changed the last bit in the subnetting portion. The broadcast address in the second subnet is going to be 16, so this one, plus 15, because we would get 15 if we switched these 4 zeros into 4 ones. So that's 10.10.10.31. Third subnet is going to go from 32 to 47. And then fourth subnet is going to go from 48 to 63. And then fifth subnet is from 64 to 79. And we can already see that the answer to our question is no. But let's look at the sixth subnet, which goes from 80 to 95. Now we're sure that these two addresses are not in the same subnet. 10.10.10.72 is somewhere in the fifth subnet, and 10.10.10.80 is the network ID of the sixth subnet. Next question. Could you allocate the address 10.10.10.96 to a router interface? A router interface is just like any other endpoint device within a network. So you can't give it a network ID or a broadcast IP address. You can allocate any other IP address within the subnet, but the network ID and broadcast IP address. So when we look at the sixth subnet, it goes from 10.10.10.80 to 10.10.10.95. You already know what that means. The network ID of our seventh subnet is going to be 96. So that's going to be a network IP address. So the answer to second question is no. You can't allocate that address to a router interface or any other device in a network. Question number 3. What's the first address you could allocate to a router or any host in that range? Of course, here we are talking about this subnet from our previous question. And as we saw in that table, this address 10.10.10.96 is a network ID. So the first usable IP address is 10.10.10.97. And that address can be allocated to a router interface or a computer or any other device on that network. So our answer here is 10.10.10.97 is the first usable IP address. Subnetting with variable length subnet masks, example number 1. A company uses address range 10.0.0.0/8 and they want to create smaller subnets, and these are their requirements. They want 2 500 hosts subnets, 1 subnet with 220 hosts, 4 50 hosts subnets, 3 subnets with 10 hosts per subnet, and then finally 2 point-to-point subnets. We're going to start off with a table, and first we're going to fill in the number of hosts required for each subnet. We're going to sort those subnets from the largest one to the smallest one. And a small disclaimer here. In each of these subnets, we're actually going to need 2 more IP addresses than is stated here. So for example, in the requirement, we're told that the first subnet is going to have 500 hosts. So we need 500 IP addresses, but then we need 2 additional IP addresses, one for network ID and one for broadcast IP address. We're going to consider this in our next example, but for now, we're going to use the exact number of hosts as the number of IP addresses that we need for each subnet, except of course for the last 2 networks, because it's really obvious that we need at least 4 IP addresses in a point-to-point network. Okay, so the first subnet is going to have a 10.0.0.0 network ID because that's what we got in the requirement, and so that's what we're starting with. This is what 10.0.0.0 looks like in the binary format, and I've underlined the first octet because that is our default network portion. We're going to use 9 bits for our host portion because that gives us 512 different combinations. If we used 8 bits, 2 to the power of 8 is 256, and that's not enough for our requirement for our first subnet. So we're going to go with 9 bits. That means our new mask is /23. 23 plus 9 equals 32, which is a total number of bits in an IPv4 address. That's how we got that number. Now let's think about the broadcast IP address. To determine the broadcast address, we need to switch all of the bits from our host portion into ones. So when we do that, we have 9 ones at the end of our IP address. So the broadcast IP is going to be 10.0. Those are the 2 first octets and they haven't changed. But the third octet has changed and that's going to be 1. And then the fourth octet is going to be 255. So the broadcast IP is 10.0.1.255. Now the range is the easiest one to determine because we're just going to go from the first address after the network ID and then up to the one address before the broadcast IP address. So we're going to go from 10.0.0.1 to 10.0.1.254. Our next subnet's network ID is just going to be the next address after the broadcast IP from the first subnet, which is 10.0.2.0. And this is what it looks like in binary format. Now we're going to use /23 mask here too, because we also need 500 hosts for this subnet. And then for the broadcast IP, we're going to switch the host bits to ones, which means that the third octet is now going to be 3 and the fourth octet is going to be 255. So the broadcast IP is 10.0.3.255. Range of usable addresses goes from 10.0.2.1 to 10.0.3.254. Network ID for the third subnet is obviously going to be 10.0.4.0, and this is what that looks like in binary format. This time we're going to use 8 bits for the host portion because 2 to the power of 8 is 256, and that's enough to fit the 220 hosts from our requirement. 32 minus 8 is 24, so that's our new mask, /24. And we're going to switch the 8 host bits into ones in order to get our broadcast IP address. So since the first 3 octets haven't changed, that's going to be 10.0.4.255. Range is easy. It's going to go from 10.041 to 10.04.254. And then our fourth subnet network ID is going to be 10.050, which is the next address right after the broadcast IP of our third subnet. Let's see what that looks like in binary format. So this is 10.050 in binary format. This time we're going to use 6 bits for our host portion, because 2 to the power of 6 is 64. So we can fit the 50 hosts into that. So that's good enough for us. If we use 6 bits for hosts, that means our new mask is going to be /26. So we have 26 network bits and 6 host bits. To get a broadcast IP, we're going to switch all of the host bits into ones. And now the value of this fourth octet is going to be 63. So our broadcast is 10.05.63. Range is as always easy. It goes from 10.051 to 10.05.62 in this example. Next subnet network ID is 10.05.64, and this is what that looks like in binary format. The mask obviously remains the same, and then to get the broadcast IP, instead of 6 consecutive ones, now we have 7 consecutive ones. So these 6 consecutive ones added up to 63, and then 63 plus 64, which is the value of this bit, equals 127. So that's our broadcast IP, 10.05.127. Range is again easy. It goes from 10.05.65 to 10.05.126. Again, our next subnet network ID is going to be the address that comes right after the broadcast IP from our previous subnet, which is in this case 10.05.128, and this is what that looks like in binary format. Mask, of course, remains the same, /26, and then for the broadcast IP, we're going to switch all the host bits into ones. These 6 ones add up to 63, and this first one is 128. So 128 plus 63 equals 191. So our broadcast IP is 10.05.191. Range of usable IP addresses go from 10.05.129 to 10.05.190. And then one more of these 50 hosts networks. Network ID is going to be 10.05.192. Mask remains the same, /26. And this is what this looks like in binary format. Broadcast IP is this time easy to calculate, is going to be 10.05.255 because we've finally filled up the fourth octet with ones. Usable IP addresses range from 10.05.193 to 10.05.254. Next subnet network ID is 10.060. Let's see what that looks like in binary format. So right now we have 5. In order to get 6, we're going to switch these 2 bits. Now we need to determine the mask. We're going to use 4 bits because 2 to the power of 4 is 16, and we only need 10 addresses, so 16 will do. This means that our new mask is /28. Now, I want to stop for a minute here and explain something further. Up until now, we've used this CIDR format for our masks, but you should know that you can't always use this format. For example, when you're configuring a router, you can't just say, here's your IP address, for example, 10.065, and then say /28 or 26 or whatever. You can't. You have to write a mask in a decimal format. So for /28, you have 28 ones and then 4 zeros. This is how masks work. In decimal format, that's 255 in the first 3 octets, and then in the last octet, we have 240. So that's what you would type in to a router if you're using a /28 mask. All right, let's move on. So to determine the broadcast IP, we need to switch the last 4 bits into ones. That's going to be 15. So the broadcast is 10.06.15, and the range goes from 1 to 14. Network ID of the next subnet is going to be 10.06.16, and this is what that's going to be in binary format. Broadcast for this subnet is going to be 31, so 10.06.31. Range goes from 17 to 30, and then the network ID for our next subnet is going to be 10.06.32. Mask stays the same, /28, and this is what that looks like in binary format. Now, broadcast is going to be 32 plus 15, which is 47. So it's 10.06.47, and then range goes from 32 to 46. Again, network ID for our next subnet is just the next IP address, and in this case, that's 10.06.48. And this is what that looks like in binary format. The mask, of course, is going to be /30, as we've discussed earlier. And then broadcast is going to be 48 plus 3, which is 51. So that's 10.06.51. As for the range, we can anyway only use 2 IP addresses, and these are 49 and 50. Finally, our last subnet network ID is 10.06.52, and this is what that looks like in binary format. The mask, of course, remains the same, /30. For the broadcast IP, we need to switch these last 2 bits into ones. When we do that, we get 55, so our broadcast IP is 10.06.55. As for the range of usable IP addresses, again, we can only use 2, and in this case, those 2 are 10.06.53 and 10.06.54. Subnetting with VLSM, example number 2. This time, we have a company that uses a public range 176.33.202.0/23. They want to create smaller subnets, and these are their requirements. 2 point-to-point subnets, 1 subnet with 100 hosts, 3 subnets where each subnet has 4 hosts, and then 2 subnets where each subnet has 13 hosts. Again, we're going to start with a table, and we're going to sort the subnets from the largest one to the smallest one. This time, I've counted in the network ID and the broadcast IP address. So instead of just copying the requirement that said we need, for example, for the first subnet, 100 hosts, I'm saying here we actually need 102 IP addresses, and same goes for all the other subnets. All right, let's dig in. So the first network ID for the first subnet is going to be 176.33.202.0. And this is what that looks like in binary format. So in the very beginning, in the requirement, we got /23 mask. So this is 23 bits that represent the network portion, and those are the underlined bits in this representation right here. Next thing we need to determine is how many host bits we're going to use to be able to create 102 different combinations. We'll go with 7 bits because 2 to the power of 7 is 128. And that is good enough for us because we need only 102. So our new mask is going to be /25. We got that from 32 minus 7. That's exactly 25. So that's the 25 network bits in our new subnet. To calculate the broadcast IP, we're going to switch these 7 host bits into 7 ones. In total, the fourth octet is 127, and since the first 3 octets haven't changed, our broadcast is 176, 33, 202, 127. Range of usable IP addresses goes from 1 to 126. And the network ID of our second subnet is going to be 176, 33, 202, 128. And this is what that looks like in binary format. So only the first bit is switched on. This first bit has a value of 128. We're going to go ahead and use 4 host bits, which means that our mask is going to be /28. 2 to the power of 4 is 16, so we are a bit tight here, but it does meet our requirements for the second and third subnet, so we're going to go ahead with 4 bits. To calculate the broadcast IP, we're going to switch the last 4 bits into 4 ones. In total, that's going to be 15 plus 128, which is 143. So the broadcast IP is 176, 33, 202, 143. And then the range goes from 129 to 142. Our next network ID is 176, 33, 202, 144, and the mask remains the same. This is what that looks like in binary format. And then when we switch the host bits into ones, we get the broadcast IP 176, 33, 202, 159. Range of usable IP addresses goes from 145 to 158. Next subnet network ID is 176, 33, 202, 160. This is what that looks like in binary format, and this time we're going to use 3 host bits. 2 to the power of 3 is 8, and that satisfies our requirements for our next 3 subnets. When we switch the last 3 bits into ones, we're going to get 167 in our last octet, so that's our broadcast IP. And then the range goes from 161 to 166. Now we're going to go a bit faster for the next 2 subnets. So first of all, the mask remains the same. It's going to be /29. And then the network ID for our 5th subnet is going to be 168. Now this is pure math. So if we can only create 8 different IP addresses in our 4th subnet, that means we can just add 8 to that network ID and get the next network ID. That's what we're going to do for our 6th subnet. So 168 plus 8 is 176. So those are the network IDs. The 6th subnet is also going to have a total of 8 IP addresses. So the next network ID for our next subnet is again going to be that network ID plus 8, which in this case is 184. Now we can cheat a little bit with the broadcast IPs. So the broadcast IP for this subnet, let me see, that's the 5th subnet. So the broadcast IP for this subnet is going to be 175 because that's network ID of the next subnet minus 1. And then the next broadcast IP is going to be 183. The ranges we don't really care about anymore. Hopefully you got how we determine the ranges of usable IP addresses. The last 2 networks are point-to-point networks. So that's even easier. We can go one by one. So network ID is 184, and then the range of usable addresses is 185 to 186, and then the broadcast IP is the next address, 187. Last but not least, network ID is going to be 176, 33, 202, 188. The two usable addresses are going to be 189 and 190. And then the broadcast IP is going to be 191. In this example, our task is to create a summary IP address. As I explained in one of the previous lessons, it makes sense to create a summary IP address when you have a lot of consecutive subnets. In this scenario here, we have 3 networks called areas. So maybe you're familiar with this terminology. If not, doesn't matter. So these are just 3 different networks. And it takes just a couple seconds to look at this scheme right here and notice that all of these subnets in area 0 are consecutive. So it's 96, 97, 98, 99, 100, 101, and 102. So in order to create one summary IP that is going to represent all of these networks, we're going to list all of them in one table. The first network is 96, and this is its binary representation. To make things easier, I put these binary values up here. So 96 is going to be 64 plus 32. So this is the binary value of the first network. The second network, 97, is going to be similar. The only difference is in the last bit. And the third network, 98, is also going to be similar, but the last 2 bits are going to switch. And then I'm just going to list the rest of them right away. Now the only thing left to determine is up until which point are these subnets the same, or up until which bit. So how many bits are the same for all of these subnets? We can determine that by looking at these numbers. So only the 3 bits in this third octet are different. All the way up to this point, all of these subnets match. So I'm just going to draw a line right here, and this line is actually going to be our new mask. We're going to copy all of the bits that match, so all of the bits from the first bit until the 21st bit, and this is going to be the 21st bit because we are in our third octet here. So this is bit number 21, this is 22, this is 23, and this is 24. So all of the bits left to the red line we're going to copy, and then all of the bits right to the red line are going to become 0. And that's actually it. We already have our summary IP. It's 192.168.96.0/21. There is one more thing I want to mention here. So there's one more IP address that isn't listed here, but it does fit into this summary IP, and that's 192.168.103.0. So you should be careful when doing this, and I'm going to show you why right now. Let me go back to the first slide. Okay, so let's imagine that this Area 2 network has a couple more routers in it, and that one of the subnets is this 192.168.103/24 network. If router 6 is configured with this summary IP, it's going to think that all of those subnets from 96 to 103 are to its left, or that they are connected to this interface right here. And if that's not the case, if this 103 subnet is somewhere to the right, then you're going to have a routing problem. But regardless, you're still going to be asked to summarize networks. And this scenario is just one of the risks that you're going to decide whether you're going to take it or not.